In this video, we're going to look at the relationship between the normal distribution and the binomial distribution, one of our discrete distributions that we've talked about in the past. Let's take a bit of a moment to refresh ourselves on the binomial distribution. The binomial distribution. Binomial distribution x. So remember, x is counting the number of successes. Number of successes in n trials. Fixing the number of trials, counting the number of successes with a success probability p. P is your constant success probability throughout these independent trials. And the probability of getting x successes in n trials is n choose x p to the x times q to the n minus x, or n choose x p to the x q is your failure probability, which is just 1 minus p. 1 minus p. 1 minus p. Okay, there we go. And so we had the binomial distribution. We've looked at this in the past, and there is a CDF table. A1, usually the first table in the appendix in the back of our textbook, gives us the probability that x is less than or equal to little x. But this only goes up to small values, only for small values of x. Small values of x up to 20. The most we can get is 20 successes. We can do 20 trials up to 20 successes. All right. And so enter now the normal approximation to the binomial distribution. Normal approximation to the binomial. To the binomial distribution. So let's say we have a random variable x. Let x be binomial with parameters n and p. Remember, you need to know the number of trials and your success probability. For large values of n, x has approximately a normal distribution. A normal distribution with mean mu equal to n times p and variance sigma squared equal to npq, or np times 1 minus p. So these are the associated parameters for approximating a binomial random variable using a normal distribution. What is the average number of successes, mu? Well, if you do n trials with a success probability of p, then you would expect n times p successes. That's our mean. And notice that this is the variance, not the standard deviation. The variance is np times 1 minus p. And so if that is approximately normal, then if you want the probability that x is less than or equal to some value little x, by definition, since x is a binomial distribution, this is discrete, then we're going to sum over all of the binomial probabilities as k goes from 0 to x. K goes from 0 to x. This is approximately equal to then the probability of, excuse me. Oh. Standard normal random variable z, being equal to, less than or equal to, x minus mu plus 0.5 over sigma. Plus 0.5 over sigma. this is very close to what it would look like to just convert a normal random variable x to a standard normal random variable z. But notice we have this x minus mu plus 0.5 over sigma, not just x minus mu over sigma. We'll talk about that 0.5 in a moment here. So for large n, it says x has approximately a normal distribution. How large does n need to be in order for this approximation to sort of be a good idea? We say that this is good. This is good if n times p and n times q, or n times 1 minus p, are both greater than or equal to 5. Are both greater than or equal to 5. We would say that this is good. All right. If n times p and n times 1 minus p are both greater than or equal to 5. About this extra plus 0.5 now in this conversion here, this is a continuity correction. The plus 0.5 is the continuity correction, because what you're doing, remember, is you are actually using a continuous distribution to approximate a discrete distribution, continuity correction. And so in the normal random variable, the idea that you can look at a value, for example, of 2.4. 2.4 is in the realm of possibility. Somewhere between 2 and 2.4 could happen in a normal random variable that's continuous. However, if you're approximating a discrete random variable that takes on integer values, like you're counting the number of heads you would get when you're flipping a coin in 10 trials, you can't get 2.4 heads. You can get either 2 heads or you can get 3 heads. All right? And so when you're using a continuous distribution, that 2.4 would essentially round down to 2. And so we would include that probability with that lower value there. So when we're adding that 0.5, this is a continuity correction because we're using a continuous distribution to approximate a discrete distribution. Let's take a look at an example using this. The probability that a patient recovers from a rare blood disease, probability that a patient recovers from a rare blood disease is 0.40. If 100 people are known to have contracted the disease, if 100 people are known to have this disease, what is the probability that fewer than 30 survive? What is the probability that fewer than 30 survive? Okay, let's take a look at what we have here. This is definitely a binomial distribution. We have n equals 100 people, and the probability that a patient recovers is 0.4. So probability of survive here is 0.40. Notice, let's see here. Notice NP, 100 times 0.4, then would be 40. That would be our mean in a normal random variable that's approximating this. What would the variance be? That would be NP times 1 minus P. So that would be 40 times 0.6. That's 24 is equal to sigma squared. 24 is sigma squared. So this is a good approximation. MP is 40. That's greater than 5 if you're looking at the condition above. Also, n times 1 minus p would actually end up being 60, which is also greater than 5. So this fits that condition that we can use a normal approximation here. What is the probability that fewer than 30 survive here? This is actually the probability that x is less than 30. X is less than 30. Okay. Now be careful when we're doing this normal approximation here. We're looking at a cumulative distribution would be less than or equal to. So fewer than 30 would be equivalent to the probability that x is less than or equal to 29. And this is important to make sure we're doing the appropriate continuity correction. If we just start at 30 and convert from there, we're looking at 30 plus 0.5, which would be too much. We really just want to include 29 up to 29.5 here. So this is approximately a normal distribution less than or equal to 29 minus the mean, which is 40, plus a continuity correction of 0.5, all over the standard deviation, which would be the square root of 24. Remember, this is sigma squared is 24, so the standard deviation would be root 24. And so we need to run that number through a calculator and look at the probability that a standard normal random variable is less than or equal to negative 2.14. Less than or equal to negative 2.14, and at this stage we can figure out that probability using the tables. We should get 0.0162. All right, how are we doing on time here real quick? Okay, good. Let's go ahead and do one more example before we wrap up this video. A multiple choice quiz has 80 questions. Each with 4 possible answers. Each with 4 possible answers. Of which, of course, only one is correct. Of which only one is correct. So we've got a... This is actually a pretty intense quiz if you've got 80 questions. 80 questions, 4 answers, A, B, C, or D. 1 answer choice is correct for each question. What is the probability? What is the probability that a random guesswork, that a random guess on every question yields from 25 to 30 correct answers? 25 to 30 correct answers. 25 to 30 correct answers. Where's the probability that random guess on every question yields 25 to 30 correct answers? So basically, you have a test, maybe you have a bubble sheet to fill in, A, B, C, or D, and the idea is you don't even look at the questions, you just fill in, random answers, and we're trying to calculate that probability. So let's go ahead and set this up here. If x is going to count the number of correct answers, then x is a binomial random variable, number of correct answers. You have 80 trials. 80 trials. Success probability per question, if we're just randomly guessing, there's 1 out of 4 correct, there's a 25% chance then, of which only 1 of the 4 possible answers is correct. So 25% chance per question that we get it correct. All right, so let's take a look here. If we're going to use a standard normal random variable, we're going to use a normal approximation, mean n times p. 80 times 0.25 is 20. And so that is good enough there. Notice n times q would be larger than that. 80 times 0.75 would be 60. And so both of these values are greater than 5. A normal approximation is a good choice here. But that aside, let's find the variance. NP times q. 80 times 0.25 times 0.75. Well, since I know 80 times 0.25 is 20, then this is just 20 times 0.75. And so that is 15. And so let's write out what we want here. What do we want? We want the probability of getting 25 to 30 correct answers. That is inclusive on your bounds. 25, 26, 27, 28, 29, or 30 are the valid possibilities. So we want the probability that X is between 25 to 30 inclusive. Inclusive. All right. And before we go into converting to a normal question, I would recommend opening this up as you would try to answer it normally, where we would say, what's the probability that X is less than or equal to 30? And then we'll subtract the appropriate probability that X is less than or equal to not 25, but this would be 24. This would be 24, because remember, X is discrete. So less than or equal to 30 would give me everything up to 30, including 25, and I want to get rid of all the answers 24, 23, 22, and below, so I'm going to start at 24. And be careful on that split, because now this does affect your continuity correction, right? Because if you put 25 here, then we're subtracting 25 from the possible answer choices, and we don't want to do that. We should allow 25 to be included, and so we're going to go less than or equal to 24. And so now we see this is approximately standard normal, less than or equal to 30 minus the mean. Add back in your continuity correction here over the standard deviation. And then the same conversion on this one, 24 minus the mean, which is 20. Add in the continuity correction and divided by the standard deviation. And that is the correct conversion. Once we run these numbers through a calculator here, we're looking for z less than or equal to about 2.71 there. 2.71 minus the probability that z is less than or equal to 1.16. And when you're computing these z values, these standard normal values on the right-hand side of your probability term, notice our table, our standard normal table, only goes to 2 decimal places. And so if it's not exactly 2.71, if it's 2.711, we can just round that to the nearest 100th place there. So round that to 2.71, for example. And so we can look up 2.71 in the standard normal table and the 1.16 as well. Double check your table skills. You should get about 0.9966 minus 0.8770. And so this is about 11.96% or 0.1196.